Come on, my dears, let us proceed further in chapter number 2. If you remembered, last time, in place of one long summation, we have adopted one symbol, capital I. And last time we had seen only the name of that quantity. Name was moment of inertia. But let me tell you that moment of inertia is defined for given rigid body when it is rotating about given stationary axis of rotation. So now let us see today very much in detail about moment of inertia. Look, short note on moment of inertia. In textbook they have not drawn any figure. If you draw this figure, try to understand, you will just remember very easily. Look, here is a rigid body, might be having any arbitrary shape. Arbitrary means at random, you can select any shape, no problem. Suppose it is rotating about this stationary axis of rotation. Fine. Its first particle is this, suppose its mass is m1, its perpendicular distance from this stationary axis of rotation is suppose r1. For second particle, mass is m2, perpendicular distance from this stationary axis of rotation is suppose r2. For the last particle, mass is mn, perpendicular distance from this axis is suppose rn. Now tell me, last time you have adopted this symbol capital I for one term, which was the term sigma mi ri square, where I indicates order of particle, which you should change from first to last. Come on, I is equal to 1 to n. First of all, put I equal to 1 here, so it will give you m1 r1 square. Here it is m1 r1 square, and because it is sigma means summation, we should write plus. After I equal to 1, we are supposed to write I equal to 2. Come on, write it here, m2 r2 square. Here it is m2 r2 square, correct? Plus dash 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 plus. Now write last order of the particle, which is n. So write here I equal to n, mn rn square. Here it is mn rn square. This summation is called moment of inertia of this rigid body rotating about this stationary axis of rotation. How would you define it in words? Let us see now definition of moment of inertia. If m1, m2, dash dash dash, mn are the masses of constituent particles of a given rigid body, and if r1, r2, dash dash dash, rn are their respective perpendicular distances from given stationary axis of rotation, then the summation m1 r1 square plus m2 r2 square plus dash 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 plus mn rn square is called moment of inertia of that rigid body rotating about that stationary axis of rotation. Full stop. This gives you definition of moment of inertia. I repeat, if m1, m2, dash dash dash, mn are the masses of constituent particles of a given rigid body, and if r1, r2, dash dash dash, rn are their respective perpendicular distances from given stationary axis of rotation, then the summation m1 r1 square plus m2 r2 square plus dash 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 plus mn rn square is called moment of inertia of that rigid body rotating about that stationary axis of rotation. Full stop. Got it? Now let us see SI unit of moment of inertia. Very simple. Look, for mass unit is kilogram, for distance square meter square, correct? So SI unit of moment of inertia is kilogram into meter square. But if you require say CGS unit, then instead of kilogram, what would you suggest? Gram. Instead of meter square, come on, centimeter square. So it would be gram into centimeter square. What about dimensional formula of moment of inertia? For mass, come on, m raised to 1. For distance square, L raised to 2. Time is not there, so T raised to 0. M raised to 1, L raised to 2, T raised to 0. Correct? Value of I depends on value of I depends on, remember, two factors. It depends on, come on, choice of axis of rotation. It depends on choice of axis of rotation, means which axis you are taking as axis of rotation. Depending upon that, value of I will change. And once you fix up the axis of rotation, after that, how is the distribution of mass around that axis? On that also value of I depends. If distribution of mass is closer to axis of rotation, naturally when the distribution is closer, all these distances would be small, and hence the summation would be less, that is value of I will be less. But if you distribute mass away from axis of rotation, then distances would increase, and when these distances would increase, come on, summation would increase, that is value of I will increase. Okay, fine. So I depends on two factors, come on, choice of axis of rotation and also distribution of mass around axis of rotation. Got it? Now there are certain formula for some regular shaped bodies having uniform density, which you must remember regarding their moment of inertia. I am showing you one by one. Here is thin circular ring, extremely thin circular ring. When it rotates about an axis perpendicular to its plane and passing through its center, its moment of inertia is I equals to mr square, where m is mass, r is radius. This formula is equally applicable for extremely thin hollow cylinder, where it rotates about its geometrical axis. At that time, its moment of inertia is also given by same formula, I equals to mr square. Okay. Now suppose this is a extremely thin circular ring which rotates about this axis which is passing through its diameter, and when it does so, its moment of inertia is 1 by 2 mr square. Come on, 1 by 2 mr square, which is half of this. Okay, just remember. Then this is a solid cylinder. For this solid cylinder, when it rotates about its geometrical axis, its moment of inertia is I equals to 1 by 2 mr square, where m is mass, r is radius. Same formula is equally applicable for a solid circular disc when it rotates about an axis perpendicular to its plane and passing through its center. At that time, this formula is equally applicable for such a body also. Then, if the same disc is now rotating about an axis passing through its diameter, then its moment of inertia is half of this. Half of this means 1 by 4 mr square. 1 by 4 mr square. Fine. Now consider this as a solid sphere, and when this solid sphere rotates about an axis passing through its diameter, at that time its moment of inertia is I equals to 2 by 5 mr square. I equals to 2 by 5 mr square, where m is mass, r is radius. And now take this as extremely thin spherical shell. It is a hollow sphere, extremely thin spherical shell. This is a hollow sphere having very thin wall, and for such a spherical shell, SHELL, spherical shell, when it rotates about an axis passing through its diameter, its moment of inertia is I equals to 2 by 3 mr square. 2 by 3 mr square, where m is mass, r is as usual radius. Now consider this as extremely thin straight rod having uniform linear density of mass. When it rotates about an axis perpendicular to its length and passing through its center, at that time its moment of inertia is 1 by 12 ml square. 1 by 12 ml square, where m is mass, l is length. Okay. Now let's go for one theoretical article. What is called radius of gyration? Radius of gyration, shown by symbol capital K. Fine. Think of a rigid body which is rotating about some axis of rotation. Now if you think that rigid body is made up of, say, identical particles, because it is made up of identical constituent particles, each particle must have same mass. So masses of all the constituent particles you can take same, let it be small m. Correct? Whether it is first particle or second or last, all of them have same mass, that is small m. Fine. Now you know formula of moment of inertia. What was that mathematical form? Come on, m1 r1 square plus m2 r2 square plus dash 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 plus mn rn square. Here it is. And now tell me, instead of m1, m2, mn, I am going to write now m. Instead of m1, come on, write m. Here also m. Here also m. M. Can I take common? Inside the bracket, r1 square plus r2 square plus dash 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 plus rn square. Now just do one thing. Multiply by n, divide by n. Multiply by n, divide by n. What is n? You know? Total number of constituent particles. Total number of constituent particles. Fine. Now tell me, what will this give you? Come on, m into n. What is m? Mass of one particle, and such n identical particles are there. So when you multiply m with n, it will give you total mass of a given rigid body. Let it be capital M. Let it be capital M. So m into n is nothing but capital M, total mass of a rigid body. But now in place of this whole bracket, I am just putting k square, not k square, wait. This bracket is replaced by k square. So immediately below this you must write where k square is how much? r1 square plus r2 square plus dash 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 plus rn square upon n. Tell me in the numerator what are you doing? You are taking summation of distances? No. Summation of squares of perpendicular distances. Summation of squares of perpendicular distances for n particles. And then you are dividing by n. So what will you get? You will get average of squares of perpendicular distances of all the constituent particles. And such an average we may show mathematically this way. Average of r square. Average of r square. Average of r square. And now take square root in all these three terms. Take square root. Square root of this will give you k. Square root of this I have written here under root. And square root of this under root of average of r square. Correct? Now this term is only known as radius of gyration of a given rigid body about given stationary axis of rotation, shown by symbol capital K. How would you define it? Square root of average of squares of perpendicular distances of all the constituent particles of a given rigid body rotating about given stationary axis of rotation is called radius of gyration of that rigid body rotating about that axis. I repeat, square root of average of squares of perpendicular distances of all the constituent particles of a given rigid body rotating about given stationary axis of rotation is called radius of gyration of that rigid body rotating about that axis of rotation, shown by symbol capital K. Okay, fine. It is some sort of distance only, so its unit is also meter or centimeter. Fine. Now, whenever you require to find out moment of inertia of a typical shaped body, you need to use two theorems. Let us study them one by one. One is called theorem of parallel axis. Theorem of parallel axis. Theorem of parallel axis. Come on. What is that theorem? I am showing you. Theorem of parallel axis. Here is a rigid body, correct? Might be three-dimensional, might be having any volume, might be having any mass, might be having any shape, no problem. Its center of mass is suppose here, and this is an axis passing through center of mass. About this axis, moment of inertia of this rigid body is suppose IC. Okay, see, you must write below I. Now consider another axis about which moment of inertia of this rigid body is suppose I. Correct? What is the formula of I in terms of IC, in terms of mass of the body, in terms of perpendicular distance between these two parallel axes? That result itself is known as theorem of parallel axis, and that theorem is this: I equals to IC plus MD square. I equals to IC plus MD square. Mind well, these two axes must be parallel to each other. Okay. One thing is sure, that this axis will definitely pass through center of mass, means it is passing through the rigid body, but this second axis which you are choosing must be chosen parallel to this, that is sure, but you may pass it through the rigid body or it may not pass through the rigid body, it may lie outside the rigid body, no problem. The condition is they must be mutually parallel and perpendicular distance between them is small d, correct? This very result is called theorem of parallel axis. Theorem of parallel axis. How would you give the statement in words? Moment of inertia of a given rigid body about given axis of rotation is equal to summation of moment of inertia of that rigid body about an axis passing through center of mass and parallel to previous axis, and the product of total mass of that body and square of perpendicular distance between those two parallel axes. I repeat, moment of inertia of a given rigid body about any axis of rotation is just equal to summation of moment of inertia of that rigid body about an axis passing through center of mass and parallel to previously mentioned axis, and the product of total mass of that body and square of perpendicular distance between those two parallel axes, full stop. This very statement is called, come on, theorem of parallel axis. I repeat for the last time, moment of inertia of any given rigid body about any axis of rotation is just equal to summation of moment of inertia of that rigid body about an axis passing through its center of mass and parallel to previously mentioned axis, and product of total mass of that body and square of perpendicular distance between those two parallel axes, full stop. This very statement is called theorem of parallel axis. Got it? Fine. Now we go for theorem of perpendicular axis. Theorem of perpendicular axis. There is no restriction for this theorem, correct? But there is a restriction for this theorem. This theorem is applicable only for, look here, planar body. Planar body means that body in which distribution of mass is limited. It is allowed only in a single plane. In practice, you may take it very thin, okay? If distribution of mass is in the single plane, it is called two-dimensional space, and that body is called a planar body. Now, say this is a planar body whose plane is right now horizontal. Now, in that horizontal plane, on the surface of this body, we just consider a pair of mutually perpendicular axes, say x and y. About x-axis, moment of inertia of this body I am taking ix. About y-axis, moment of inertia of this body I am taking as iy. Now, consider third axis, which is not only perpendicular to these two axes, but also perpendicular to surface or plane of this planar body. Let it be z-axis. Then about z-axis, what is the moment of inertia of this body? Let it be iz. According to this theorem, this value of iz is found to be equal to summation of ix and iy. Iz equals to ix plus iy. This very result is called theorem of perpendicular axis. How would you give the statement in words? Moment of inertia of a given planar body about an axis perpendicular to its plane is just equal to summation of moments of inertia of that body about two mutually perpendicular axes lying in the same plane of the body. This very statement is called theorem of perpendicular axis. I repeat, moment of inertia of a given planar body about an axis perpendicular to its plane is just equal to summation of moments of inertia of that body about two mutually perpendicular axes chosen in the plane of the body. Correct? Fine. Now kindly read this statement of sum number 6, illustration number 6. Read it? Come on. We are given globe of earth, which right now we should take as solid sphere of uniform density, and when it rotates about an axis passing through its diameter, is having radius r1 right now, and all of a sudden what happens that it shrinks, its volume decreases, radius decreases, and it becomes all of a sudden half of the initial value. Final radius is half of initial radius. Fine. Then what have they asked? What will be the new length of the day? That is what we have to find out. Look, because the change in volume, change in radius takes place very suddenly, very briskly, you can apply law of conservation of angular momentum. In the absence of resultant external torque, total angular momentum of this body should remain constant. Now tell me, what was the formula for total angular momentum of a rigid body? Last time we had obtained, it was L equals to I omega. When I into omega remains constant, meaning that by mathematically I1 omega 1 equals to I2 omega 2. What is capital I? Moment of inertia of a solid sphere about an axis passing through its diameter. According to formula, it is 2 by 5 mr square. Here it is, 2 by 5 mr square. Remember? Fine. Same formula I am applying here, 2 by 5 mr square. But because here it is I1, I am putting here R1. Omega 1 as it is, I2. It is the moment of inertia of same earth in the final condition where its radius has become R2. So I should write 2 by 5 m R2 square, omega 2 as it is. Now you may have a question, mass will not change? No, mass will not change. What does mass give you? Mass gives you measure of quantity of matter contained in a body. That quantity of matter is not going to increase, not going to decrease, because quantity of matter is constant, naturally mass would remain constant. One thing will be there, because of shrinkage, because of decrease in volume, density would increase, but mass will remain unaffected. Fine. 2 by 5 m is getting cancelled from both the sides. R1 square omega 1 as it is, R2 square omega 2 as it is. R1 square omega 1 as it is, but what is R2 square from here? What is R2 square? R1 square upon 4, here it is, R1 square upon 4 into omega 2, correct? Now, R1 square will cancel, transfer this. So, omega 2 will be equal to 4 into omega 1. Omega 2 equals to 4 into omega 1, correct? Fine. What is omega? Angular speed is also given by formula 2 pi by capital D, where capital D is called periodic time of rotation, that is time taken by earth to complete one rotation about its own axis of rotation. Come on, omega 2 will be 2 pi upon T2, 4 as it is, omega 1 is 2 pi upon T1. This is present periodic time, this is later periodic time. Fine. Now come on, 2 pi will cancel. Find out T2, it will be T1 upon 4. T2 will be T1 upon 4. T1 upon 4. What is capital T1? Present periodic time means time taken by earth to complete one rotation about its own axis. Right now at present, you know it is 24 hours divided by 4. 24 upon 4, it will give you 6 hours per day. 6 hours per day. So a day will be having new length. How much? Only 6 hours. How much? Only 6 hours. Okay. Mind well, you may be given some other condition. Suppose radius is getting double. Suppose because of sudden expansion, radius is getting double. So what you should write here? R2 equals to 2R1. R2 equals to 2R1. Then here R2 square will be 4R1 square. And then in that case, T2 will be, come on, 4T1. T2 will be 4 into T1. 4 into T1 means 4 into 24. That is 96 hours per day. Correct? If earth expands, then length of the day would increase. If earth shrinks, length of the day would decrease. Correct? Fine. Now let us finish one more theoretical article which may be getting asked in the numericals also. Okay? You must prepare it nicely. We have one extremely thin straight rod having uniform linear density of mass which rotates about an axis perpendicular to its length and come on passing through its center. About that axis, how much is its moment of inertia? We have to derive its formula. Okay. Just do one thing. Take the length to be small l and because the centroid of this rod we take exactly on the origin, right hand side axis is positive x-axis, left hand side axis is negative x-axis. The left end of the rod has x coordinate x equals to minus L by 2, right end of the rod has x coordinate x equals to plus L by 2. Because total length is L, half of that would be L by 2, here also L by 2, but because this end lies on negative x-axis, x coordinate must be negative. This end lies on positive x-axis, x coordinate must be positive. Now just do one thing, you divide this whole mass into extremely small mass elements, and one such mass element as a specimen I have shown here having length say dx, which is chosen at perpendicular distance x from this axis of rotation. The mass contained in this mass element I am taking dm. Okay, tell me, for any linear body which density you will think of? You will think of linear density of mass. So linear density of mass I am taking as lambda. It is nothing but total mass upon total length. Total mass I am taking capital M, total length I am taking small l, and whatever mass you are writing in the numerator, corresponding length you must write in the denominator. Mass contained in this mass element is suppose dm, and length of this mass element is dx. Fine. Now take this mass element, such a small one, such that mass contained in that element can be taken as a single particle. If this can be taken as a single particle, then you know whenever any single particle is rotating about axis of rotation at perpendicular distance x suppose, then its moment of inertia about that axis is mass into square of perpendicular distance. Mass into square of perpendicular distance. Mass is dm and square of perpendicular distance is x, so it is dm into x square, dm into x square. This will give you partial moment of inertia, because we are not taking the entire length of the rod right now, we are taking only this much length, which is a part of the total length. That's why I am putting here partial moment of inertia, symbol is di. Di as it is. What is dm from here? Find out dm from here, transfer this. So m upon l into dx, m upon l into dx into x square. Fine. Take integration on both the sides, integration on both the sides. Integration di, m upon l is constant taken out, integration x square dx, integration x square dx. Now you know lower limit of integration means smallest value of variable, upper limit of integration means highest value of variable. Here variable is x, its lowest value is at left end, which is minus L by 2, x equals to minus L by 2, and the upper limit of integration means highest value of the variable. Highest value of this variable x is at right end, which is x equals to plus L by 2, x equals to plus L by 2. And when you shift this mass element right from left end to right end continuously, you are going to incorporate all the mass elements, and then if you are finding moment of inertia, it will give you moment of inertia for whole rod about an axis passing through its center perpendicular to its length. Correct? Fine. Summation of partial values of moment of inertia will give you total moment of inertia, m upon l as it is, but integration x square dx is x cube upon 3. Integration x square dx is x cube upon 3. Remember the formula? Integration x raised to n dx. What is it? X raised to n plus 1 upon n plus 1. So here it is x cube upon 3. X cube upon 3. That is x raised to 2 plus 1 upon 2 plus 1. And from minus L by 2 to plus L by 2. Minus L by 2 to plus L by 2. This m as it is, 3 because it is constant can be taken out. 3 into L in the denominator. And now instead of x, I am supposed to write upper limit, that is L by 2. It's a cube. After putting minus sign, I am supposed to write lower limit, that is instead of x, I should write minus L by 2, and then it's a cube. Now this is L cube upon 8, and here it is minus L by 2 whole cube will be minus L cube upon 8. That minus and this minus will become plus L cube upon 8. L cube upon 8 plus L cube upon 8, it is 2 L cube upon 8. And now simplify. Come on, 1 L is getting cancelled. So left here it is L square. 2 4s are 8, 4 3s are 12. So it is now m into L square upon 12. M into L square upon 12. I repeat, 2 4s are 8 and 4 3s are 12. 1 L is getting cancelled. So left here in the numerator is L square. M into L square upon 12. This gives you moment of inertia of extremely thin rod having uniform linear density of mass when it rotates about an axis, passing through its center and perpendicular to its length. Got it? Come on, my dears, let us proceed further in chapter number 2. Kindly read this statement of illustration number 8. Come on, have you read it? Tell me what is given to us. Extremely thin solid circular disc which is rotating about an axis, passing through its center perpendicular to its plane. And at that time we are asked to find out moment of inertia of that disc about that axis. Let us find out. Come on. Here is extremely thin circular disc. Whenever any object is given to you which is very thin, you can think of planar body, that is two-dimensional body. And in case of two-dimensional body, you are supposed to consider surface density of mass. Let it be sigma. It is total mass upon total area. Total mass of this disc I am taking capital M, and total surface area for a disc of radius capital R. What is surface area? Come on, pi r square. Area of a circle is pi into radius square. Correct? Fine. Now what I do? I just divide this whole surface area into extremely large number of extremely thin concentric circular rings, and one such a specimen ring I have shown in the figure with the white color. It is this ring. Okay, fine. For this ring, its surface area I am taking as dA. Come on. Area of extremely thin circular ring, remember, it is by formula inverse circumference into thickness. Circumference into thickness. If this radius is x, then circumference of a circle having radius x is 2 pi x into thickness. This much thickness is dx. This thickness is dx. So circumference into thickness will give you area of extremely thin circular ring. Okay. For this ring, I just take mass as dm, which is mass of mass element, and this is area of area element. Let it be dA. Whatever mass you write in the numerator, the mass, that much mass is contained in whichever area, that area you should write in the denominator. Okay. You must put the values correspondingly. Okay. Here this is the mass of the whole disc, then this is the surface area of the disc. Okay. And because it is extremely thin, you can just consider area of a circle. Okay. Fine. Now what is moment of inertia of this ring about this axis of rotation? Come on. For extremely thin circular ring, its moment of inertia about an axis passing through its center perpendicular to its plane is, you know by formula, mass into radius square. Mass into radius square. Mass is dm, radius is x, and it's a square. So it is now dm into x square. Fine. What is the value of dm? Find out from here. Find out dm. Take this here. So m upon pi r square into dA. Come on, m upon pi r square into dA into x square. Fine. di as it is, m upon pi r square as it is. What is the value of dA right now? dA is 2 pi x dx. dA is 2 pi x dx into x square. And now tell me, pi ones are pi, getting cancelled. Just rearrange it properly. 2m upon r square. 2m upon r square. X into x square, x cube dx. Correct? Now take integration on both the sides. Integration di. And here when you take integration, this part is constant, taken out. Integration x cube dx. Integration x cube dx. Correct? But you know the lower limit of integration means minimum value of variable, and upper limit of integration means maximum value of variable. Come on. When you take this ring at the center, minimum value of x at the center would be 0. That's why lower limit is 0. And when you increase this variable x continuously, and when you just bring that ring over here, if you consider ring at the edge of the disc, then maximum value of x would be this much. This much means just equal to radius of the disc. So maximum value of x at the edge of the disc is equal to radius of the disc. X maximum equals to capital R. So maximum value of x is capital R. This integration x cube dx from 0 to capital R. Now integration of di, summation of partial moments of inertia will give you total moment of inertia, that will be capital I. This part as it is. Integration x cube dx is nothing but x raised to 4 upon 4 from 0 to R, from 0 to R. Come on, this part as it is, but 2 2s are 4. So I am writing m upon 2r square, m upon 2r square, and here it is x raised to 4, but I am supposed to put the upper limit first. So in place of x you just write capital R whole raised to 4. After putting minus sign, instead of x you should write 0, 0 raised to 4, that is 0. Now 1 r square is getting cancelled from numerator and denominator. So left is now 1 by 2 m r square, 1 by 2 m r square, correct? This is nothing but moment of inertia of common solid circular disc, which is very thin, whose mass is m, radius is capital R, about an axis passing through its center perpendicular to its plane, correct? In this case, we are asked to find out the radius of gyration also. Come on, what we have achieved here? I equals to half mr square. We have obtained this formula, I equals to half mr square. But you know, in general, for any rigid body, for having any shape, any volume, correct? No problem. As long as it is having uniform density, you can write I equals to mk square. General formula of I for any rigid body having uniform density, come on, I equals to mk square, where k is called radius of gyration. So instead of I am putting mk square, right hand side as it is, m getting cancelled. K square will be r square upon 2. When k square is r square upon 2, take square root, k equals to r upon root 2. This is radius of gyration for this extremely thin solid circular disc. Okay, fine. Now kindly read this statement of illustration number 9. Come on, have you read it? Look, consider a planar body like this, which is extremely thin solid circular disc. Now an axis which is perpendicular to the surface of the disc is this z axis. Okay, fine. And now this is x axis, this one is y axis. Now you can think of this axis which is passing through diameter of the disc. You can think of this axis also, which is also passing through diameter of the disc. This axis is x axis, this axis is y axis. Now tell me, according to theorem of perpendicular axis, come on, in the last period we have seen Iz equals to Ix plus Iy, Iz equals to Ix plus Iy. These are the moments of inertia about those axes which are taken in the plane of the planar body. Fine. Now tell me here, moment of inertia about z axis is nothing but moment of inertia of this disc about an axis passing through its center perpendicular to its plane, and such moment of inertia just now we have derived, it is half mr square. So this Iz is half mr square, and whatever is the value of Ix, same is the value of Iy. Ix equals to Iy. Why? What is the reason? See, this is also axis passing through diameter of the disc, and this is also axis passing through diameter of the disc. For any disc about any axis which is passing through its diameter, moment of inertia would be same. So whatever is the value of Ix, same is the value of Iy. Just put up all these values in this equation. Come on. Iz is half mr square. Iz is half mr square. But in place of Iy, I can write Ix. Write it here. Ix plus Iz, that is 2Ix. Correct? Find out Ix. Take this 2 in the denominator. Correct? So come on, 1 by 4 mr square. Ix will be 1 by 4 mr square. Ix equals to 1 by 4 mr square. And same is the value of Iy also, because Ix equals to Iy. Okay? Kindly read this statement of illustration number 10. Come on, read it. Look, we are given extremely thin hollow cylinder for which moment of inertia is I equals to mr square. What is mass? 4 kilogram. Radius is 0.1 meter. It's a square. Correct? Now tell me, this into this, answer is 0.04. SI unit of moment of inertia. For mass it is kilogram. For radius square, that is meter square. Come on, kilogram into meter square. Torque formula, tau equals to Rf sin theta. Come on, here instead of small r, I am putting capital R, which is radius of that thin hollow cylinder. Come on, instead of this F as it is, instead of theta, I am putting 90 degree. Because, see, this is along radius and this force is exerted along tangent. And for a circular edge, come on, radius and tangent are mutually perpendicular. So, angle theta is 90 degree. Come on. Radius is right now 0.1 meter. Come on, this force is 50 Newton. Sin 90 is 1. This multiplication comes out to be 5. Unit of torque is Newton into meter. Newton into meter. Now, we are asked to find out angular acceleration. Don't you know very small formula? Tau equals to I alpha. Tau equals to I alpha. Torque is, come on, 5 Newton into meter. I is moment of inertia 0.04 kilogram into meter square. Alpha we require. Value of alpha comes out to be 125. You must remember unit of angular acceleration, radian per second square. Radian per second square. We are asked to find out angular velocity at the end of 4 seconds. Come on. Omega equals to omega 0 plus alpha into t. First equation of rotational motion performed with constant angular acceleration, that was omega equals to omega 0 plus alpha t. Come on. Because the body starts from rest, initial angular velocity is 0. This alpha has come out to be 125. What about time given to you is 4 seconds. 125 into 4, answer is 500. Unit of angular velocity is radian per second. Okay. Come on, angular momentum of a rigid body, L equals to by formula I omega. Value of I we have found out 0.04 kilogram into meter square. Value of omega at the end of 4 seconds, come on, 500 radian per second. Because this value you are putting at the end of 4 seconds, naturally you will get angular momentum also at the end of 4 seconds. This into this, answer is 20. Unit of angular momentum is joule into second. Had it been linear momentum, then Newton into second. Angular momentum, then joule into second. Fine, joule into second. Remembered how? Tau equals to dl upon dt. Tau equals to dl upon dt. So dl will be tau into dt. Tau into dt. Unit of torque you may write joule. Unit of dt, that is second. Simple. Come on. Come on. Now they have asked rotational kinetic energy. Remember the formula for linear kinetic energy. Formula for linear kinetic energy, it was half mv square. Half mv square. Don't you know, similar to mass, there is moment of inertia in rotational motion. Similar to linear speed, there is angular speed in rotational motion. So this is half mv square, this is half I omega square. Please remember this formula. Anytime I am asking you, what is the formula for rotational kinetic energy, you must tell me half I omega square. Come on, 1 by 2 I. Moment of inertia, come on, 0.04 kilogram into meter square. Value of omega at the end of 4 seconds, we have found out 500 radian per second, it's a square. Simplify, answer is 5000. Unit of energy is joule. Come on, angular displacement in 4 seconds. Let us find out using this formula. Theta equals to omega plus omega 0 upon 2 into t. What is the value of omega at the end of 4 seconds? Come on, 500 radian per second. We have found out 500. Because the body starts from rest, initial angular speed is 0 divided by 2. This time is given to you 4 seconds. Simplify, answer is 1000. Unit of angular displacement is radian. Symbol is small rad. Don't put any full stop. Come on, according to work energy theorem, work done is equal to change in rotational kinetic energy, because we are discussing rotational motion. And here change in rotational kinetic energy means final rotational kinetic energy minus initial rotational kinetic energy. Now this final rotational kinetic energy, it is 5000 joule minus initial rotational kinetic energy is 0, because initially body was at rest. 5000 minus 0, that is 5000. Unit of work is joule. Come on, now they have asked at the end of 4 seconds the instantaneous power, not average power, instantaneous power. Instantaneous power has this formula, P equals to tau into omega. If they ask suppose average power, you may find out work done upon time taken. Work done upon time taken. Okay. Right now it is not average power, it is instantaneous power. So formula is P equals to tau into omega. What is torque formula? Torque value? We have found out 5 Newton into meter. 5 Newton into meter. Value of omega at the end of 4 seconds. Come on, 500 radian per second. Into 5, that is 2500. Unit of power is watt. Correct? Fine. Now in first semester you have studied some quantities, some equations for linear motion, and similar or analogous quantities and equations you have studied right now in second semester. So let us make a comparison. Okay. So let us see the parallelism between linear motion and rotational motion. Come on, linear displacement. Here, come on everybody, angular displacement. Initial linear velocity, initial angular velocity. Come on, final linear velocity, final angular velocity. You know linear acceleration is time rate of change of linear velocity. Similarly here angular acceleration is time rate of change of angular velocity. Come on, mass is similar to moment of inertia. Linear moment of vector P equals to m into vector v. Here angular moment of vector L equals to I into vector omega. Linear momentum is analogous to angular momentum. Mass is analogous or similar to moment of inertia. Velocity, linear velocity is similar to angular velocity. Come on, vector F equals to m into vector A. Come on, here vector tau equals to I into vector alpha. Force is similar to torque. Mass is similar to moment of inertia. And linear acceleration is similar to angular acceleration. Come on, linear kinetic energy by formula half mv square. Here rotational kinetic energy half I omega square. Come on, instead of mass we find here capital I, that is moment of inertia. Linear speed is similar to angular speed. Okay. Come on, work done formula in case of linear motion, force into displacement, and in case of rotational motion, work done formula is W equals to tau into theta. Force is similar to torque, linear displacement is similar to angular displacement. Correct? Fine. P equals to F into V. This is instantaneous power, it is force into velocity. This is instantaneous power in rotational motion, it is torque into angular velocity. Come on, force is similar to torque, linear velocity is similar to angular velocity. And now let us see equations of linear motion. Here V equals to V0 plus AT, here omega equals to omega 0 plus alpha t. Here D equals to V0 t plus half AT square, here theta equals to omega 0 t plus half alpha t square. Here V square minus V0 square equals to 2 AD. Here omega square minus omega 0 square equals to 2 alpha theta. Here D equals to V plus V0 upon 2 into T. Here theta equals to omega plus omega 0 upon 2 into T. Just tell me the similarity. Here initial linear speed, here initial angular speed. Final linear speed, final angular speed. Constant linear acceleration, constant angular acceleration. Correct? And here this is average linear velocity, this is average angular velocity. Okay, fine. Now kindly read the statement of number 11, illustration number 11. Come on, read it. Tell me. We are given one turntable and that turntable is rotating about an axis passing through its center perpendicular to its plane with angular speed say omega 1 in the initial condition. There is a man who is standing at the edge of the turntable, and now what does he do? He moves. He walks over the surface of this turntable, he moves and he comes here at the center. And final angular speed, if it is omega 2, it is how much? That's value we have to find out. First of all, tell me, because on this entire system there is no resultant external torque, then according to law of conservation of angular momentum, we can say total angular momentum must remain constant. What is angular momentum of a rigid body? L equals to I omega, and that should remain constant. What is the mathematical meaning of I omega being constant? When I into omega is constant, come on, I1 omega 1 equals to I2 omega 2. 1 1 means initial condition, 2 2 means final condition. Come on, in the initial condition, what is total moment of inertia of entire system? For this disk, you know the formula, it is half mr square, correct? But when you treat this man as a particle of mass small m, and because he is at perpendicular distance capital R from this center, then his moment of inertia would be m into r square, mass into square of perpendicular distance, correct? This perpendicular distance is equal to radius of the turntable. Radius of the turntable, I am taking capital R. This radius is capital R, correct? Fine. Now tell me, mass into square of perpendicular distance. This much is the moment of inertia of that person into omega 1. What about I2? I2 is the moment of inertia of the same system in the final condition. But in the final condition, this person has come at the center. When the person has come at the center, his distance from this stationary, from this axis of rotation would be 0. Because he himself at the center, when he is at the center, his perpendicular distance from this axis would be 0. When that perpendicular distance is 0, the moment of inertia of this person would become 0 in the final condition. So for turntable is concerned, its moment of inertia remains as it is. Earlier also it was half mr square, now also it is half mr square. For person it has become 0. Final angular speed we are looking for, that value is omega 2. Come on. Throughout the equation, what you can cancel? Capital R square. Here, from here and from here. You can get it cancelled. Left here it is capital M by 2 plus small m. Omega 1 as it is. Here capital M by 2 into omega 2. Come on, capital M is mass of turntable 200 kilogram upon 2. Mass of person is 60 kilogram. Omega 1 is initial angular speed. You are given 20 rpm, rotations per minute. Rotations per minute. This capital M is 200 kilogram, that is mass of turntable upon 2, omega 2 as it is. And now find out value of omega 2, it comes out to be 32 rpm, rotations per minute. Because omega 1 you are taking in rpm, naturally omega 2 will be obtained in rpm. But suppose we require to convert into radian per second, how would you? Come on, omega 2 is right now 32 rpm, rotations per minute. If you want to convert into radian per second, remember, multiply by 2 pi divided by 60, because one rotation is 2 pi radian divided by 1 minute. 1 minute is 60 seconds. So multiply by 2 pi divided by 60. Put y value 3.14. Simplify, answer is 3.349 radian per second. Now let us convert initial angular speed also from rpm to radian per second. What was initial angular speed? Omega 1, it was, come on, 20 rpm. Convert into radian per second, multiply by 2 pi upon 60. Pi value is 3.14. Simplify, answer is 2.0933 radian per second. Now at the end of this solution in the textbook, they have made an extra note, and in that extra note they have suggested to find out increase in rotational kinetic energy when this person he walks from edge to the center. In this process, what is the increase in rotational kinetic energy? That thing they have asked to find out by taking radius of turntable as 1.5 meter. Let us find out. They may ask in the school examination. Okay, fine. Let us calculate this thing extra. change in rotational kinetic energy, it is final rotational kinetic energy minus initial rotational kinetic energy, half I2 omega 2 square minus half I1 omega 1 square. Let me take 1 by 2 common. Let me take 1 by 2 common. Look, 1 by 2 if I take common, then inside the bracket, come on, I2 omega 2 square minus I1 omega 1 square. Correct? Fine. So this is half into I2 omega 2 square minus I1 omega 1 square. Come on. This 1 by 2 as it is. 1 by 2 as it is. Correct? What is I2? What is I2? I2 is, come on, half mr square. I2 is half mr square into omega 2 square minus, what is I1? I1 is this much. The same bracket I have written here without any change. Half capital M capital R square plus small m capital R square into omega 1 square. Got it? And now tell me, this R square I just take out. I am taking out only R square. So when I have taken out this R square here, it will be, come on, R square by 2. R square by 2. What is left here? Capital M by 2 into omega 2 square. R square has gone out. Capital M by 2. R square has gone out. Small m into omega 1 square. Now just dictate me all the values. Radius of turntable, they have suggested to take 1.5 meter, square of it divided by 2. This is mass of turntable 200 kilogram upon 2. This is final angular speed in radian per second, we have found out 3.349. It's a square minus mass of turntable 200 kilogram, mass of person 60 kilogram, initial angular speed in radian per second, we have found out 2.0933. 2.0933 radian per second, it's a square. Okay, simplify that many joule. This is change in rotational kinetic energy. It comes out to be positive, meaning thereby there is increase in the rotational kinetic energy, because when this man walks from here to here, he does some work on the turntable, and because work is done, the energy of the system has increased. Okay. Kindly read this statement of sum number 12. Come on, read it. Again we are given one solid circular disc which is rotating about an axis passing through its center perpendicular to its plane. Fine. Suppose this disc is rotating with angular speed omega. Here lies one child whose mass is m. Initially this child is at perpendicular distance 1 meter from this axis of rotation. Okay. Now when the angular speed of this disc is gradually increased at a particular angular speed, say at omega, it so happens that this child starts sliding outward this way, correct? Radially outward. What is that minimum angular speed for which the child would start sliding outward? That omega value we have to find out. Come on. This child has mass m, so naturally gravitational force exerted on this child in vertically downward direction would be mg. This much is the force exerted by child on the disc in the form of force of action and perpendicularly downwards. Now in just opposite direction there would be force of reaction provided by disc on the child in just opposite direction, and because this force of reaction is exerted perpendicular to the contact surface, we call it normal force, shown by symbol capital N. During the motion, this child remains under equilibrium along this vertical axis. So whatever is vertically upward force, same must be vertically downward force. N must be equal to mg. Come on, N must be equal to mg. Correct? Now tell me, because this child is sitting on the disc which is itself rotating, correct? You know, rotating frame of reference is always having some acceleration, and now when this child is in accelerated frame of reference, it will experience, come on, pseudo force. Whenever any object lies in accelerated frame of reference, it would experience pseudo force, and that pseudo force is always opposite to real force. For circular motion, come on, real force is pointing towards the center, and then that is the real force which is pointing towards the center, and pseudo force is opposite to real force. Opposite to this means like this, correct? Real force is pointing towards the center, pseudo force is pointing away from center, correct? Fine. If real force is pointing towards the center, that is centripetal, then the pseudo force is pointing away from center, it is centrifugal, centrifugal. Come on, in this direction there is a pseudo force. Now, under the influence of this pseudo force, when this child would start sliding outward, there would be force due to friction in just opposite direction, and so this is the frictional force. And what is the frictional force formula? Coefficient of friction multiplied by normal force. Coefficient of friction is mu, normal force is n. And now tell me, when this child is about to slide outward, at that time this force and this force must have become equal. So when you increase the angular speed gradually, come on, this pseudo force will increase. Why? What is the formula for pseudo force? Mass of a body on which pseudo force is exerted multiplied by acceleration of accelerated frame of reference. Right now, the acceleration for uniform circular motion, you must be knowing, it is radial acceleration. It has three formula: omega into v, omega square r, and v square upon r, out of which I am using this formula omega square r, correct? Mass into radial acceleration would give you force. Right now it is away from the center, it is pseudo force. Fine. Now m is constant, r is constant, but as you increase omega gradually more and more, naturally when omega will increase, this part will increase, so this force will increase, and at a moment when this force becomes equal to this force, at that very moment child would be about to slide. He will be on the verge of sliding, correct? At that time this force has become equal to this force. M omega square r equals to mu into n. M omega square r equals to mu into n. Come on, this part as it is, mu as it is, n equals to mg. Come on, n equals to mg. M will cancel. Find out omega square, it is mu into g upon r. Mu into g upon r. Take square root on both the sides. Square root of this is omega. Square root of this is under root of mu g upon r. What about coefficient of friction? They have given 0.25, g value 10 meter per second square, and this is not the radius of the disc. No, no, no. Right now it is the perpendicular distance of this child from this axis, which they have given as 1 meter. So this radius of circular path followed by the child is 1 meter. Simplify, answer is 1.581 radian per second. Mind well, at this angular speed of the disc, child has not slided. He is on the verge of sliding, okay, he is about to slide. But now when you increase the angular speed beyond this, naturally child will start sliding outward. He will be thrown out of the disc, okay. If angular speed is smaller than this, then child will remain on the disc. When angular speed is equal to this, child is on the verge of sliding outward, and when the angular speed is more than this, child will definitely slide outside, correct? Fine. Now read the statement of number 13. Come on, read it. We are given one solid circular disc of mass capital M, radius capital R. It is capable of rotating about an axis perpendicular to its surface and passing through its center. Fine. And here we have wrapped some rope, and at the lower end of that rope or string, we have tied one body, say block of mass small m. When we release this block, it so happens it starts sliding downwards, correct? It starts moving downwards with some acceleration, say A. So this is the acceleration of this block when it moves downwards. Okay, fine. On a body of mass small m, what is downward gravitational force? It is mg. And now when this body is tied at the end of the string, naturally this string will remain stretched under tension. And you know, forces due to tension are always produced at the endpoints, equal in magnitude and pointing towards each other. Correct? So this force is also T, this force is also T. Now this force is becoming now tangential force because it is exerted in the direction of tangent at this very point, which is in contact with this disc. That's why the tangential force will produce rotational motion in this disc. Okay, fine. Come on, for this block, downward force must be more, then only it is moving downwards with some acceleration. So take greater force minus smaller force. Greater force is mg, smaller force is t. Greater minus smaller will give you resultant force, that would be mass into acceleration. Mass into acceleration. Find out t now. Transfer this from minus to, it will become plus. Transfer this part here, from plus it will become minus. Then take m common, inside the bracket g minus a. Now for disc, come on. For disc, come on. Because it is performing rotational motion, there must be some torque exerted on the disc. You know formula of torque? Tau equals to Rf sin theta. Instead of small r, I am putting radius of disc, which is capital R. Instead of f, I am putting capital T, which is tangential force. And sin theta, theta is 90 degree. Come on, angle between this position vector and this force, you can see it is 90 degree. Theta is 90 degree. Come on, this R as it is. What about capital T? It is m into g minus a. Capital T is m into g minus a. Sin 90 is 1. And now tau equals to I alpha. Tau equals to I alpha. Now tell me, what is A here? See here, this force is exerted tangentially. It would produce tangential acceleration, and tangential acceleration by formula, you know, it is alpha into R. Alpha into R, instead of small r, I am writing capital R. I repeat, because this is tangential force, it would produce tangential acceleration, and that tangential acceleration by formula, it is alpha into R. Come on. A equals to AT equals to alpha into R, put it here. Moment of inertia of a solid circular disc about an axis passing through its center perpendicular to its plane is half mr square into alpha, that equals to capital R into m into g minus a. Instead of a, I should write R into alpha. R into alpha. Simplify now. One R is getting cancelled. What is left on the left side? M R alpha upon 2, M R alpha upon 2. This M as it is, just multiply inside, mg minus M R alpha. Come on, transfer this part over here, from minus it will become plus, and then take R into alpha common. Here, left inside the bracket from here, it is capital M by 2, and when you transfer this term over here, from minus it became plus, so left inside the bracket from here, it would be small m. And this mg as it is, I want only alpha, so this capital R and this bracket I must transfer on the right hand side in the denominator. Just find out alpha, it would be mg upon R into this bracket has come in the denominator. Okay, so value of angular acceleration can be found out for using this formula. This is the angular acceleration of this disc. Okay, fine. Come on, my dears, let us proceed further in chapter number 2. Today we will study two very important theories. Now, first theory is regarding planetary motion, that is motion of any planet around sun. It was Mr. Kepler, the famous astronomist, who had devised 3 laws on planetary motion, out of which we are going to prove today second law. What is that Kepler's second law? The same result is also giving you geometrical interpretation of law of conservation of angular momentum. How I am showing you. Look, before obtaining Kepler's second law, let me show you what is that result. The result is something like this. Suppose this is the position of sun, okay, and every planet revolves around sun in an orbit which is of such a shape which is called elliptical orbit. Elliptical orbit. At one of the two foci of that elliptical orbit, Sun is located, and say this is the planet who is revolving around that Sun. At a particular instant of time, suppose planet comes over here at point P1. Fine. Join Sun and planet. Okay, you will get this line. And after some time, say delta t, after delta t time, suppose the same planet comes over here. Again join Sun and planet by this line. Okay. So this is the area, this is the shaded area, which is area traversed or area swept by line joining Sun and planet in time delta t. Okay. Now after some time, suppose planet appears over here at point P3. From that point onwards, just allow it to move for same time interval which you had taken earlier, delta t. And after delta t time, suppose planet comes from P3 to P4. Again find out this area swept by line joining Sun and planet. Then after some time, the planet comes at point P5. Again let it be allowed same time delta t to move further. Suppose it comes at point P6, and again you find out this area swept by line joining Sun and planet. You know what Mr. Kepler had proved? He proved that all these three areas which are swept in equal intervals of time are equal. Areas swept by line joining Sun and given planet are equal in equal intervals of time. This very result is known as Kepler's second law. Every time if area is swept at the same rate, then you can say aerial velocity remains constant. Aerial velocity means area traversed or area swept in unit time. It is called aerial velocity. So aerial velocity of different planets might be different, but for a given planet over its entire orbit, that aerial velocity remains constant. This result was derived by Mr. Kepler. In his regards, we call it Kepler's law. Okay. Let us obtain that law now. Look, here is position of Sun. S indicates position of Sun. And this is the elliptical orbit, part of the elliptical orbit of a planet who comes at point P at time t on this path of motion. Fine. And at time t, when it comes here, it has instantaneous velocity in the direction of tangent drawn to this path of motion at this very point in this direction. And in whichever direction there is a velocity, come on, linear momentum also is in the same direction. Vector P equals to m into vector v. Fine. Now, when planet is here, the gravitational force exerted by Sun on this planet is in this direction. Correct? Fine. So this is line of action of force. And this Sun is lying exactly on the line of action of force, then no torque is developed by such a force on this planet because Sun is lying on the line of action of force. Recall the formula of torque, tau equals to Rf sin theta. If reference point is lying on the line of action of force, don't you know, theta will be either 0 or 180 degree. In both the cases, sin theta would be 0. Tau equals to Rf sin theta is 0, so torque will be 0. So there is no torque exerted by this force on this planet. Whenever there is no torque on any system, its total angular momentum would remain constant. So angular momentum of this planet should remain constant. Come on, angular momentum I am showing by symbol L, that should remain constant according to law of conservation of angular momentum. Come on. What is angular momentum? We had proved in the earlier part of this chapter, we had proved angular momentum is moment of linear momentum. Moment of linear momentum means linear momentum multiplied by perpendicular distance. What is linear momentum of planet at time t? It is m into v, correct? Multiplied by perpendicular distance of line passing through vector p from given reference point. This is the line passing through vector p. This is the line passing through linear momentum vector, and find out perpendicular distance of this line from this reference point, that is from sun. Find out perpendicular distance. Just draw one perpendicular from sun onto this line. That perpendicular distance would be SQ, and that SQ perpendicular distance I have shown by symbol small d. That's why I have multiplied by small d. This is linear momentum. This is perpendicular distance of line passing through direction of linear momentum from reference point, that is d. And such a product is going to give you moment of linear momentum, which is called angular momentum, shown by symbol capital L. And because there is no torque exerted on this planet, its total angular momentum should remain constant. Okay. Now suppose area of this triangle SQP is suppose capital A. Let me find it out. Come on, area of triangle SQP, suppose it is A, I want to find it. What is area of a triangle? Half base into height. Half base into height. Come on, 1 by 2. What is this base from here to here? This base is PQ. Let it be shown by symbol small s. Come on, base is small s, and this is the perpendicular. Half base into height. Height is d. Half base into height. Okay, fine. 1 by 2 into s into d. This is going to give you area of triangle SQP. Now, after point P, suppose at the end of delta t time, after time t, that is at time t plus delta t, suppose this planet comes from P to P2, from P to this point, which is P2. In time delta t, suppose planet moves from here to here. Planet moves from here to here. This is the point on the path of motion of planet. Okay, let it be P2. In short, planet moves from here to here in time delta t. Fine. Now you just do one thing, join sun and this position P2, and then just extend that direction, extend that line forward, and let it intersect here, and this point which is lying on the vector small p is suppose P1. So this point is P1 and this point is P2. This point is P1, this point is P2. Now tell me, find out the area of this triangle SQP1. Come on, SQP1. Fine. Come on, area of triangle SQP1. It is area of this triangle plus area of this part. Okay. Come on, when you add these two areas, suppose this much area, additionally it is delta A. This additional area I am showing by symbol delta A, and this area is capital A. So if I want total area, I should add these two. Come on, A plus delta A. It is going to give you area of triangle SQP1. Area of a triangle, half base into height. Half base, base is this much. This much means this much plus this much. What is this? Come on, S. What is this? Increase in the value of S. Let it be delta S. So from here to here, this total distance is S plus delta S. S plus delta S into height. Height is this much, which is perpendicular distance. It is small d. Fine. Now just take the subtraction. Take the subtraction. This minus this. AA will cancel, giving you delta A. This minus this. Which part you can take common? 1 by 2d. 1 by 2d. You can take common. 1 by 2d common. Inside the bracket, this minus this. SS will cancel, giving you delta S. Divide on both the sides by delta t. Fine. And now tell me, I am taking limit delta t tends to 0 on both the sides. Come on. Take here limit delta t tends to 0. So here it is limit delta t tends to 0. Delta A by delta t. Here 1 by 2d is constant. Limit delta t tends to 0, delta s by delta t. Limit delta t tends to 0, delta s by delta t. See, I must take limit delta t tends to 0. Why? Tell me. Actually, these points P1 and P2, they are not same points. They are different points. We were supposed to find out area of part SQP2. But instead of SQP2, we had found out area of triangle SQP1. How can you do that? Provided these 2 points are very close to each other. If these 2 points have to be very close to each other, then the time interval which you had allowed to the planet to move from P to P2, that time interval should be reduced as small as possible. Then what will happen? If limit delta t tends to 0, if you are allowing extremely small time interval, then points P1 and P2 are very close to each other, and when they are very close to each other, then instead of P2 we may write P1. Okay? For that sake, you must take limit delta t tends to 0 on both the sides. Now in the language of calculus, this part is nothing but dA by dt. What is it? dA by dt. 1 by 2d as it is. What is this part? In the language of calculus, this is ds by dt. dA by dt as it is, 1 by 2d as it is. Time rate of change of position of a planet. Time rate of change of position of a planet is going to give you its instantaneous velocity. Instantaneous velocity of this planet at time t is vector v. Magnitude wise it is v. Okay. So this gives you instantaneous speed of the planet, which is v. And now tell me, just multiply on both the sides by m, that is mass of the planet. Just multiply here, m into dA by dt, 1 by 2 as it is, multiply by m into v into d, m into v into d, correct? Now this part as it is, 1 by 2 as it is, what is this m into v into d? What is this m into v into d? What is it? Capital L. Come on, this part is nothing but capital L, which is angular momentum of planet. Take this m down. So dA by dt would be L upon 2m. L upon 2m, correct? Now tell me, here angular momentum is constant. Angular momentum is constant. So L is constant and mass of a given planet is definitely constant. So this part will remain constant. So dA by dt is constant. Come on everybody, dA by dt is constant. What is this? dA by dt means what? Denominator you should think 1 unit. So this is nothing but area swept in unit time. Area swept in unit time by a line joining sun and planet. That area swept in unit time is called aerial velocity of a planet, and that aerial velocity of a planet remains constant. Aerial velocity of planet remains constant. This very statement is called, come on, Kepler's second law on planetary motion, correct? Tell me, when you say that angular momentum is constant, meaning thereby angular momentum is conserved, because L is constant, then only you could write dA by dt is constant, correct? So you are using law of conservation of angular momentum, and ultimately you are getting aerial velocity constant, and that aerial velocity is constant, meaning thereby area swept in unit time remains same. Might be here, might be here, might be here. Everywhere area swept in unit time remains same, and the same fact you are showing here in the figure. When you show anything, any fact in the figure, it is geometrical interpretation. What is it? Geometrical interpretation. So geometrical interpretation of law of conservation of angular momentum is that the area swept in unit time is constant, which is nothing but Kepler's second law. So either you say Kepler's second law or you say geometrical interpretation of law of conservation of angular momentum, the theory, the final result remains same. Okay, fine. Just speak out for the last time. Kepler's second law of planetary motion. Aerial velocity of every planet remains constant. This statement is called Kepler's second law. For different planets, aerial velocity might be different, but for a given planet, it remains constant. Okay. One thing more. See here, dA by dt is constant. dA by dt is constant. That's what we have proved. dA by dt is constant. So let me write here constant. This dA by dt is constant. If dA by dt is constant, tell me. When this is constant, 1 by 2 is constant, so V into D should remain constant. V is the velocity, D is the distance from sun. Now tell me, when this product is remaining constant, what does it mean? When distance is maximum, velocity will be minimum. Speak reverse, when distance is minimum, velocity will be maximum. How to find this position? On this elliptical orbit, this position is the farthest having maximum distance. If distance is maximum, velocity will be minimum. So when planet is passing through this point, its velocity is minimum. And when the same planet comes here, this is the position which is closest to the sun. So distance is minimum. When distance is minimum, that time velocity is maximum. Velocity is maximum. Okay, fine. Now we go for next theory. That is the last theory in the chapter. Very important. Look at the title. Condition to roll down the slope of angle theta without sliding, without slipping. Condition to roll down the slope without slipping. What can be that condition? I am showing you. Condition to roll down the slope of angle theta without slipping. Look, consider a slope. Okay, here is the slope. This is the surface of slope. This is the base of the slope. This much is the height of the slope. The distance between point at the top and point at the bottom on the surface of slope gives you length of the slope, which is from point A to point B. That length of the slope is AB, which is suppose small d. An angle made by slopy surface with the horizontal is called angle of slope. Let it be theta. I repeat, what is h? Height of slope. What is d? Length of slope from here to here. And what is theta? Angle of slope. Okay. Just think of a body at the top of the slope which can roll down the slope without slipping. Now first of all, think, what do you mean by rolling without slipping? What do you mean by rolling without slipping? I am showing you. Just put a sphere, solid sphere here, okay? Just release it. When you release it, come on, it starts rolling down the slope this way. At that time, its a center of mass. Earlier it was here, now it is found to be here, later on might be here. So center of mass performs motion on a straight path. Means it performs linear motion. The whole body performs rotational motion. Correct? Both the motions are carried out at a time. Linear motion also, rotational motion also. Now you can define the meaning of rolling without slipping. I am showing you. Whenever any body performs rotational motion and at the same time, due to that rotational motion, if its center of mass performs linear motion, then that body is said to be rolling without slipping. I repeat, whenever any body is performing rotational motion and at the same time its center of mass performs linear motion due to that rotational motion, then that body is said to be rolling without slipping. For example, in the cricket game, when one inning is over, the groundman comes with the heavy roller and he just pushes that roller ahead on the pitch. That heavy roller, which is a very big drum, very big cylinder, it is pushed forward this way. At that time, the whole roller, look here, it is performing rotational motion. And at the same time, its center of mass is pushed forward this way. Performs linear motion, correct? Due to that rotational motion. At that time we say roller is, come on, rolling without slipping. Rolling without slipping. Because it is horizontal surface, we have to push the roller. Here, because it is a slopy surface, we don't have to push, we simply have to release this body. Okay, but both the cases, body is rolling without slipping. I repeat, whenever any body is performing rotational motion and at the same time its center of mass performs linear motion due to that rotational motion, then that body is said to be rolling without slipping. Come on. Say here is a body of mass small m, radius capital R, lying at the top of the slope at rest. Because it is at rest, initial kinetic energy is 0. And you know, whenever a body of mass m lies at height h with respect to some reference level, then its gravitational potential energy with respect to that reference level is mgh. Fine. Now release this body. When you release this body, it starts performing rolling motion without slipping. It comes at the bottom of the slope. Fine. At the bottom of the slope, suppose the final velocity is v, final angular velocity is suppose omega. Don't you know v equals to r omega, correct? Fine. Now because the body has performed two types of motion, one is linear motion, another is rotational motion. Due to both the types of motions, it will have some kinetic energy. Kinetic energy due to translational motion, it is half mv square. Due to rotational motion, it is half I omega square. And the summation will be half mv square plus half I omega square. This is total kinetic energy achieved by the body when it comes at the bottom of the slope. And because it has come at the bottom, the height of this body from this bottom would become 0. When h is 0, the whole part will be 0. Then gravitational potential energy of the body at the bottom would be 0. So by the time body comes from top to bottom, what has happened? Its gravitational potential energy has been decreased, and at the cost of gravitational potential energy, there has been increase in its kinetic energy from 0 to this much. So if you apply law of conservation of mechanical energy, then you can say loss in potential energy should be equal to gain in kinetic energy. Loss in potential energy should be equal to gain in kinetic energy. What is loss in potential energy? From mgh it has become 0. So loss in potential energy is mgh. And what about gain in kinetic energy? Gain in kinetic energy is this much. Look, this minus 0. Correct? So gain in kinetic energy is half mv square plus half I omega square. Fine. mgh as it is, half mv square as it is, 1 by 2 as it is. Do you know the formula of moment of inertia in terms of radius of gyration? You must remember I equals to mk square. Instead of capital M, right now mass of this body we have taken according to textbook small m. And what about omega square? Find out omega from here. Omega will be V upon R. Omega will be V upon R. Omega is V upon R. So what is omega square? V square upon R square. Come on, omega square is V square upon R square. Half mv square, half mv square. Can you take common? Yes. Inside the bracket, left from here, inside the bracket is 1. And come on, half mv square has gone out. Left inside the bracket from here, it is k square upon r square. K square upon r square. Fine. M will cancel. Find out v square. Transfer these two. So it is 2gh upon 1 plus k square upon r square. Give it equation number 1. Recall third equation of linear motion with constant linear acceleration. Come on, v square minus v0 square equals to 2ad. Because this body started from rest, initial velocity is 0, v square as it is, 2a as it is. What about d? Find out d from here. First of all, tell me, if you find out sine theta in this right angle triangle, if you find out sine theta, what is sine theta? Opposite upon adjacent. Opposite upon hypotenuse. Opposite upon hypotenuse. Opposite to theta, what is it? H. Here it is. Divided by hypotenuse, that is opposite to right angle, which is from A to B. And A to B, the distance is called length of the slope. It is small d. Opposite upon hypotenuse. Opposite upon hypotenuse is sine theta. Find out d from here. D will be h upon sine theta. Come on, d will be h upon sine theta. Come on, this d is how much? H upon sine theta. Correct? Give it equation number 2. And now match 1 and 2. Left hand sides are same. So right hand side also must be same. This must be equal to this. Come on, 2AH upon sin theta. Here it is. 2AH upon sin theta should be equal to this. Come on, 2GH upon 1 plus K square upon R square. H1 is a H, 2 1 is 2. Find out A. Transfer this. So it will be G sin theta upon 1 plus K square upon R square. Come on, G sin theta upon 1 plus K square upon R square. You know what is this A? You know what is this A? Acceleration obtained by rolling body. Acceleration obtained by rolling body. It is G sin theta upon 1 plus K square upon R square. Take LCM here. It will be R square plus K square upon R square. Denominator will become numerator. So it is now R square upon R square plus K square into G sin theta. Now tell me, here as this body is rolling down this way, correct? In just opposite direction, at the contact surface, there arises force due to friction, and that frictional force is present. So there is some deceleration in the motion of this body. There is some decrease in the acceleration of the body. If this frictional force is not there, this body would have achieved acceleration parallel to the surface of the slope. How much? In first semester you have studied acceleration of a body parallel to surface of slope. How much it is? G sin theta. How much? G sin theta. Here instead of G sin theta, the body achieves only this much acceleration. Okay. So if you want decrease in acceleration due to frictional force, you should subtract this from this. Come on, acceleration that could have been obtained in the absence of frictional force would be G sin theta, but really acceleration obtained is this much. If I subtract this from this, come on, then what will I get? Decrease in acceleration due to friction. Okay. In the absence of frictional force, this much acceleration could have been obtained. In the presence of frictional force, this much acceleration is really obtained. So what is decrease in acceleration? It will be G sin theta minus this. Come on, subtract this from this. G sin theta minus R square upon R square plus K square into G sin theta. Take G sin theta common. Then inside the bracket take LCM. R square plus K square will be multiplied here minus R square upon R square plus K square. R square will cancel. K square upon R square plus K square. K square upon R square plus K square into G sin theta. This is not acceleration, decrease in acceleration. If decrease in acceleration is this much, what would be frictional force? Frictional force is nothing but mass of a body multiplied by decrease in acceleration. Decrease in acceleration. Decrease in acceleration is this much. K square upon R square plus K square into G sin theta. Mass into decrease in acceleration is going to give you frictional force shown by symbol small f. What about normal force? Tell me. This is the body of mass m. On a body of mass m, there is downward gravitational force. How much? Mg. And I say now, if this angle is theta, this also will be theta. Why? Angle between two given line segments and angle between their perpendiculars are always equal. Perpendicular to this is this. Perpendicular to this is this. So angle between these two perpendiculars also must be theta, correct? This is theta, this also must be theta. Now resolve this vector into two mutually perpendicular components. Come on, this vector plus this vector will give you this vector, correct? Fine. Component of mg adjacent to theta. Component of mg adjacent to theta. How much it is? Mg cos theta. Component of mg opposite to theta. How much it is? Mg sin theta. This mg sin theta, instead of showing over here, I have shown it here, correct? From here to here. Fine. And now tell me, mg cos theta is the force of action provided by this rolling body onto the surface of the slope in a direction perpendicular to surface of the slope in the form of force of action. Then this surface will provide force of reaction in just opposite direction. But you know, force of reaction provided onto the body in a direction perpendicular to contact surface is called normal force. It's called normal force. So right now this is the normal force, and along this axis this body remains under equilibrium. So whatever is this force just is the opposite force. N must be equal to mg cos theta. N must be equal to mg cos theta. So we know from first semester also we know N equals to mg cos theta, correct? Now take the ratio. This upon this will be this upon this. Come Come on, f upon n, f upon n. But when you take this upon this, m into g will cancel. Sin theta upon cos theta is tan theta, and this bracketed part I have written as it is. Fine. Find out f upon n from here. You know this frictional force is coefficient of friction multiplied by normal force. Coefficient of friction, here I have taken mu s into capital N, that is normal force. If f equals to mu s into n, find out f upon n, f upon n. F upon n would be mu s. Here it is. F upon n is nothing but mu s, and that equals to this much. But what I have done here, tan theta as it is, just numerator and denominator divide by k square. When you divide by k square here, k square upon k square is 1, k square upon k square is 1, and here I have written r square upon k square. Okay. Tan theta as it is, just divide numerator and denominator by k square, you will get this term, and f upon n is nothing but mu s. You know what do we find practically? Whenever value of coefficient of static friction is greater than this, at that time also body can roll without slipping. So if you want to write the condition in a general way, then you should combine mu s equal to and mu s greater than. Both the conditions you should combine, and the combined condition can be written this way: mu s must be greater than or equal to this, that is 1 upon 1 plus r square upon k square into tan theta. When mu s is this much, at that time also body can roll without slipping, and when mu s is greater than this, then also body can roll without slipping. So combinedly, mu s must be greater than or equal to 1 upon 1 plus r square upon k square into tan theta. This is the required condition for any rigid body having radius capital R, having radius of gyration capital K, to roll down the slope of angle theta without slipping. Got it? Fine. Now you might wonder that why I put here mu s. Though this rolling body is in motion, why I have put here mu s? Why not mu k? Why only mu s? Try to understand. Look. Suppose this is the surface. This is the surface of the slope. And suppose this is the rolling body. So when it is rolling, look here this way. Correct? This way. Correct? You may think of infinite number of lines on the surface of this cylinder. Correct? But out of infinite number of lines, tell me, at a time, at a given point of time, only one line comes in contact with the slope of the surface. I mean surface of the slope. Only one line is coming in contact with the surface of the slope. Only one line, correct? Then when any one line is coming in contact with the surface of the slope, just for a moment it can be considered to be at rest relatively. And then very next moment it comes in motion, correct? Third moment it comes to rest. Fourth moment it comes in motion. Fifth moment it comes to rest. Sixth moment it will come in motion, like that. So every time little jerk is given, and it is rolling down the slope. So as if it is starting its motion every time from the position of rest. Because motion is started every time from the position of rest, I must write here coefficient of static friction. That's why I am putting mu s. Okay, fine. Look, now we are going to use this condition for three bodies which they have taken into consideration in textbook also. First, let us take thin circular ring. For thin circular ring, what would be the form of this condition? I am showing you. For thin circular ring, don't you know moment of inertia formula? I equals to mr square. But I is also equals to mk square. What is capital K? Radius of gyration. Come on, will cancel. R square equals to k square. Take this k square down, r square upon k square will be 1. Put it here. R square upon k square is 1. 1 plus 1, 2. 1 by 2, tan theta. 1 by 2, tan theta. Correct? So condition for thin circular ring is mu s must be greater than or equal to 1 by 2 tan theta. Then only it will roll down the slope of angle theta without slipping. What about condition for solid cylinder or for a solid circular disc? Come on. Moment of inertia formula is half mr square, and I formula in general is also equal to mk square. Come on, compare these two. Will cancel. R square upon 2 equals to k square. R square upon 2 equals to k square. find out r square upon k square, it will be 2. And put the value of r square upon k square, which is 2, over here. When you put it here, 1 plus 2 is 3. 1 upon 3 tan theta. 1 upon 3 tan theta. This is the condition for solid cylinder to roll down the slope of angle theta without slipping. Come on, let us take now last one, solid sphere. Come on, for a solid sphere, what is the moment of inertia formula? I equals to 2 by 5 mr square. And don't you know, for every body, I is also equal to mk square. M will cancel. 2 by 5 r square equals to k square. 2 by 5 r square equals to k square. Find out r square upon k square, it will be 5 upon 2. 5 upon 2. And put this value of r square upon k square, 5 by 2, over here. Just put it here. 5 by 2. 1 plus 5 by 2 means it is 2 plus 5, that is 7 by 2. But 7 by 2 is there in the denominator. Take this 2 up. So 2 by 7 tan theta. 2 by 7 tan theta. Here it is. 2 by 7 tan theta. This mu s greater than or equal to 2 by 7 tan theta gives you condition for a solid sphere to roll down the slope of angle theta without slipping. Okay. Thank you.